In this chapter, we're going to learn calculus and the linear algebra really briefly because in order to understand machine learning algorithms and theories, we need some background from calculus and linear algebra. So we cannot cover all the concepts and ideas. So I selected a few theories and equations from calculus and the basic stuff from linear algebra. So this is the outline of this chapter. So from calculus, we're going to talk about the derivative and Taylor series and the function minimization. And from the linear algebra, we're going to learn some basic stuff, vector operations and matrix, and eigendecomposition, classic decomposition, and derivatives of vector and matrix. First, calculus. It's not comprehensive. Okay, so first thing is the derivative, and before derivative we have to talk about the function f. So given input value x, the function f returns an output value f of x. This is a function. I think you are already familiar with this. And derivative measures the sensitivity of f of x with respect to a change in x. So when the x is just a scalar, okay, then if the function looks like this, then the derivative gives us this slope of this tangent line. Here are two famous examples. Derivative of exponential function is this exponential function itself. And the derivative of log of x is 1 over x. Okay, and I think you're already familiar with this chain rule too. And you don't have to worry about driving all these derivatives by yourself. If you are not confident, if you are confused with these derivatives, then you can check this website and you can get the correct answer. Okay. And the second one is Taylor series. Taylor series is really important, especially when we talk about optimizations or some things. Then we'll talk about Taylor series. Okay, and the Taylor series of f of x. In that case, f of x should be infinitely differentiable at a specific location. Then the Taylor series of f of x can be summarized like this. If we unfold this summation, we have f of x and the first derivative and second derivative and third derivative. Okay, but important thing is that this Taylor series of this function is polynomial equations. That is quite important because no matter how complicated the function f is, if we take a Taylor series, then we can approximate the function with the polynomial equations at a specific location. So in this example, this is function f of x. Okay, and if we take the first term of this Taylor series, okay, if we ignore all the other terms, then an approximation is just constant line. Okay, this is the evaluation of function f at the specific location a. Okay, and now if we take the first two terms, as you can see, this is a linear equation with respect to x. Okay, so now this one is this line, linear line. So if you look at this line at a specific range, okay, then this line approximates these blue curves quite good. If the range is small, then the approximation is quite good, but if we enlarge the range, then the approximation goes wrong. These are errors. Okay, And if we include one more term, then we have a quadratic equation to approximate the function f. Then around a, the approximation is better than before. Okay, so if we move away from a, then when x is around here, but still the error is not that huge. Okay, so if we increase the number of terms, then this approximation will get more accurate, especially around this a. Okay, so when the function is really complicated, then we're going to use Taylor series, especially focusing on the first couple of terms. And many times we are going to use the first two terms or the three terms. So that is important thing. So in engineering, when the problem is really complicated, then we approximate the problem with some assumptions, right? So when our approximation is good enough, then when we solve the approximated problem, then our solution is close to the actual solution, the real solution. But the approximation is not close to the real function, then the solution from the approximated problem is not close to the real solutions. So approximating the problem is quite important here. It makes the problem easier, and also the approximated the problem is still close to the real problem. Function minimization or maximization is a common problem in calculus. Okay, it is trying to find the minimum value of function f of x by moving x. So in this figure, this is the minimum. This is the minimum value, and this is the optimal x. And in the optimization chapter later, we're going to learn how to minimize or maximize the function. And when we maximize, sometimes we have constraint. By the way, the minimization is the same as maximization. So it's basically the same problem. So we're going to focus on the maximization here. So when we maximize the function, then sometimes we have a constraint. So we can formalize this problem like this. We want to maximize the function f of x. In this case, x is a two-dimensional vector, so we have two scalar values with a constraint this. So when we maximize this function, we have to satisfy this constraint. Okay, there's the problem. And there are two different cases. Okay, so first one is the easy approach. So if possible, sometimes it is possible. So if possible, we solve the constraint equation and express x1 as a function of x2. So which means this function is a simple. Okay, then we can express x sub 1 as a function of x sub 2. Okay, we can do that. Then we can replace x sub 1 in this function with this. So now we have only x2 as a variable. Okay, so it's a simple problem. So we can maximize this with respect to x sub 2, and then we find the optimal value for x sub 2, and then we can reuse this function to find the optimal value for x sub 1. So this is a simple case. But most of the time in machine learning, this is not possible. Okay. So it would not be possible to find an analytic solution. Okay, in that case, we can use Lagrange multiplier. Now let's talk about Lagrange multiplier, which is quite popular in machine learning. So you're going to see this a lot in this semester. Okay, so let's start from this constraint. G of x is 0. Okay, this constraint makes a, a surface in high-dimensional space. So in the previous slide, x was two-dimensional. Okay, so now we have a two-dimensional surface like this. But we can generalize this into a high-dimensional space. Okay, so given this constraint, and we want to move slightly. So we have x here. This is x on the surface, and we want to move slightly on this surface in this direction or in this direction. But anyway, either way will be fine. So this is a linear. Okay, so we have x plus epsilon. So in this case, epsilon is also a vector, right? Now, g of x plus epsilon can be rewritten with the Taylor series. But in the Taylor series, we have lots of terms, but we ignore all the other terms. We just take just first two terms. Okay, it's kind of approximation again. And then actually the third term is based on epsilon transpose epsilon here. Okay, then epsilon is supposed to be quite small. So epsilon transpose epsilon is approaching to 0. Okay, and then since epsilon is on this surface, so g of x plus epsilon is the same as this one is a 0 and this one is also 0. So this one should be 0. And this equation says epsilon is orthogonal to this gradient of g. And then now gradient of g is normal, basically orthogonal to this constraint, because epsilon is parallel to this surface. Epsilon is this direction. Okay, and then epsilon is orthogonal to this one. You know, when the inner product between these two vectors is 0, then this one and this ones are orthogonal. Okay, so epsilon is orthogonal to this one, and epsilon is parallel to this surface, then this one should be orthogonal to this surface. Okay, so now we got this direction. Okay, gradient of g is orthogonal to this surface. Okay, then gradient of f should be also orthogonal to this surface, otherwise it can maximize on the surface. So this gradient is in this direction. Okay, which means in this surface we can maximize this function. So that is not actual optimal solution. So we don't have optimal solution in that direction. So this one should be also orthogonal to this surface. Now we got this direction, and this direction and these directions are on the same line. So when we have lambda here, then we can have this equation. Okay, so from this knowledge we can build up one new function named Lagrange function. So Lagrange function is actually our objective function f of x plus lambda times constraint function. Okay, and we call lambda Lagrange multiplier. Then when we take a derivative of this Lagrange function with respect to x, then it should be 0. Okay, then it leads to this term. This one is coming from this. And when we take a derivative of this Lagrange function with respect to lambda, it leads to the constraint surface. This one is coming from this. So we just defined the Lagrange multiplier with the Lagrange function in the previous slide. Then we can use this with the actual problem, actual equations. let's maximize f with the constraint g when the f of x is like this and the g of x looks like this. Okay, so given these two equations, when we build up a Lagrangian function, then it looks like this. This one is coming from here, and this part is coming from here. Okay, then we take a derivative of this Lagrange function with respect to x1, then we have this equation. When we take a derivative with respect to x2, then we have this term. This is quite a simple kind of derivative. And also we take a derivative with respect to lambda, then we have this. They should be 0, basically. We have 3 variables with the 3 equations, so we can solve the problem. Okay, now we have x1 and x2 and lambda here. Okay, this is how we use a Lagrange multiplier. Jensen's inequality is also a popular one in machine learning. Okay, so given a convex function, Jensen's inequality says this. So let me explain what convex function is. Okay, so this function is not a convex function, and this function is convex because when we pick 2, x1 and x2, then we evaluate the function f at the 2 locations. Then if we draw a line between these two, then this line is lower than this curve. Okay, but sometimes if we pick 2, x1, x2 here, then when we draw a line, then this line is above this curve. But sometimes this line is lower than actual curve. So if we have this kind of line, then this is not a convex function. But in this case, wherever you pick 2 values for x1 and x2, then if we draw a line between these two, then this line is above this actual curve. And if we pick 2 here, then if we draw a line, then this line is above the actual curve. Okay, so this is convex. So when the function is convex, and then the function of this is lower than or at least equal to this for any t. T is between 0 and 1. Look at this one. This one is actually weighted sum of x1 and x2. And this one is weighted sum of f of x1 and f of x2. Okay, so this one is here. So tx1 plus 1 minus t times x sub 2 is one point between x1 and x2. Okay, it could be any point here. Okay, so let's say now current one is here. And then we evaluate the function at this point. Then this one is the function of this point. This one is same as this one. And the second term says the weighted sum of this function of x1 and the function of x2. So function of x1 is here, and function of x2 is here. So it's function x1. Okay. Then this one says the weighted sum of these two values with the t and 1 minus t. Then actually this one is the right hand side of this inequality. So this inequality says quite a simple concept. So if the function f of x is convex, then no matter where you pick to x1 and x2, then actual function value of this weighted sum is always lower than the weighted sum of two function values. Okay, so which means when the curve is like this, then this one is always above this actual curve. And if the function is a concave, if it is like this, then the inequality sign should be flipped. Okay, like this. And in probability theory, we're going to use this one a lot, like this. This one is a function, and this one is weighted sum. And this one is weighted sum, and this one is function. So when we change the order of this function and expectation, then we have this inequality. So we're going to see this one a lot.